Hello linear algebra students. This video lesson is on the topic of eigenspaces. Compute the following transformations and then plot the input and output vectors. This linear transformation in both cases is the same. You can recognize that because they have the same standard matrices. In the first case, we input the vector 1, -1, and then we perform this matrix vector multiplication to get the output. So for the first component, we'll get 3 minus 2, which is 1. And the second component will get -2 plus 2, which is 0. So plotting both the input and the output vector, let's let the input vector be green, 1, -1, and the output vector will let be red. And you'll notice from the imagery that the red vector is not in the span of the green vector, which means to say that the red vector is not a multiple of the green vector. Now let's take a look at the second input-output pairing. Inputting the vector -2, 1, and then multiplying that vector to this standard matrix, we get as the first component -6 plus 2, which is -4, and then 4 minus 2, which is 2. Plotting both the input and output vectors here, the input vector is -2, 1, and the output vector is -4, 2. In this case, we notice that the output vector is actually a multiple of the input vector. And specifically in this case, it's a doubling of the input vector. Now, when this phenomenon happens, that is, matrix vector multiplication has the effect of doing a scalar multiple of the input vector, then we have some special terms for the scalar and for the input vector. This scalar 2 here is called an eigenvalue, and this input vector is called an eigenvector. Now, eigenvectors have to be non-zero vectors, but eigenvalues can be any real number. Furthermore, notice that if I were to plug into this transformation any scalar multiple of this eigenvector, for example, let's plug in its opposite, which is 2, -1. Doing the matrix vector multiplication, in this case, we get 6 minus 2, which is 4. And then we get -4 plus 2, which is -2. And notice once again, we get a doubling of the input vector. So this 2 is still our eigenvalue, but now we have a different example of an eigenvector. What we're going to see in a moment is that when there is an eigenvalue, such as 2, that there will be infinitely many possible eigenvectors that correspond to it. In fact, any multiple of that eigenvector is another example of an eigenvector associated with that eigenvalue. Okay, let's go to the next page. On this page, we're going to focus on how to find eigenvalues for a square matrix. As stated on the previous page, the eigenvalue of a square matrix A is a scalar R such that there exists a non-zero vector x, called an eigenvector, that satisfies the statement below. So this statement amounts to doing a linear transformation on x. We have some square matrix times x, and if the result is simply doing a scalar multiple of x, then R will be called an eigenvalue, and x, provided it's a non-zero vector, is called an eigenvector associated with that eigenvalue. Now, manipulating this equation, let's subtract Rx from both sides. Keep in mind that this is a vector equation, so when you subtract a vector from the right side to zero out that right side, you have the zero vector over there. Now I'm going to factor out x, and I have to factor it to the right side. And currently what I have written is an incoherent statement. Notice that we have a matrix A minus a scalar R, which is not a possible operation. We can easily get around this issue by putting the identity matrix right here, so that we have a matrix minus a matrix. And notice that when you distribute the x back through, the identity times x will just be x again. Now keep in mind that we want a non-zero solution to this, and we have a square matrix sitting right here. So we can tap into our theory on square matrices. If a square matrix times a vector equals a zero vector, and we want a non-zero solution to that, this tells us that the square matrix has to be singular, so its determinant must be equal to 0. This is called the characteristic equation, and we are going to solve it to find the eigenvalues of a matrix A. Find the eigenvalues of the matrix below. Now notice this matrix here is the same square matrix that we examined on the previous page. And we had evidence already on this previous page that this 2 right here is an eigenvalue. The question is, are there others, or is this the only possible eigenvalue for this matrix? Okay, we do this work by setting up the following equation. We say that 0 must be equal to the determinant of this matrix A minus R times the identity matrix. So this gives us 0 equals, the matrix A is 3, negative 2, 2, negative 2. And then we're going to remove from this R times the identity matrix. And of course, we want this to be an appropriately sized identity matrix. So in this case, it would have to be I sub 2, a 2 by 2 identity matrix. Multiplying the 2 by 2 identity matrix by R simply puts R's on the main diagonal. And then we can subtract these two matrices before I calculate determinant, which effectively amounts to removing R from the main diagonal of A. So here's R removed from the main diagonal of A, and then the other two entries are unchanged. And now we calculate this 2 by 2 determinant. So we do the product of the main diagonal, and then minus the product of the other two entries. And we simplify this expression. We FOIL, giving us negative 6 minus 3R plus 2R plus R squared. And then we have minus negative 4, so plus 4. And then continuing to simplify, we have R squared minus R minus 2. Notice this is just a quadratic equation, so we expect up to two distinct answers. Maybe repeated answers, maybe imaginary answers. In this case, our quadratic factors, R minus 2 and R plus 1. So this suggests that we have two different possible eigenvalues, 2 and negative 1. These are the only two eigenvalues associated with this matrix A. Now for some terminology, this polynomial right here is called the characteristic polynomial. But when we set it equal to 0, this is what we were calling the characteristic equation. Equation implies that there's an equal sign. Now if A is a 2 by 2 matrix, this will imply that we will produce a second degree polynomial, which means that we expect no more than two distinct eigenvalues. Now for short, instead of writing out eigenvalues, it's common to write evals. So now reading right here, note that if A is n by n, then there can be no more than n distinct eigenvalues. So the size of A can be used to know ahead of time the maximum number of distinct eigenvalues. Okay, let's go to the next page. This page focuses on how now to find the corresponding eigenvectors. Each eigenvalue R of a square matrix has infinitely many corresponding eigenvectors, found by solving the system below. This equation you see right here is simply this variant of this relationship, where we want A times some non-zero vector to be equal to simply a scalar times that same non-zero vector. Now we have to do this for each eigenvalue. So the eigenvalues that we found from the previous page were negative 1 and 2. I'll go in order from least to greatest. So working first with R equals negative 1. We begin by setting up A minus Ri times some vector x equals the 0 vector. And then we substitute this eigenvalue into this equation. And we get A plus the identity matrix times some vector x must be equal to the 0 vector. And then I'm going to convert this to an augmented matrix, where we first do A plus I. So we have to add the identity matrix to the matrix A, which really means add 1 to the main diagonal. So the main diagonal will become 4 and negative 1, and the other two entries will not be any different. So this is our coefficient matrix times some vector x equals a 0 vector. So we can put this in augmented matrix form and put the 0 vector on the other side of the equal sign. And then we put this in reduced row echelon form, giving us 1, 1/2, 0, 0, 0, 0. Now because r equals negative 1 is a value for which A minus Ri is singular, it means that we do expect to have free variables. This vector x is in R2, so we have two components of it, x and y. The only pivot position is right here, which means that y is free. Now the first row would read x plus 1/2 y is equal to 0. We'll solve that for x and say x has to be negative 1/2 of y. And y is free, so we'll say this y equals itself. And we have one free variable. Thus, our solution will be any vector of the following form. The x has to be negative 1/2 times y, and y is itself. We can factor that y out and say basically any multiple of the vector negative 1/2, 1 will be a eigenvector. And I should say any non-zero multiple will be an eigenvector. Well, this is effectively the span of a vector. All multiples of negative 1/2, 1 form a subspace. Therefore, I can use as a basis for that subspace any non-zero vector in that subspace, including the non-zero vector that we simply see above. However, you can switch the basis to any basis that's convenient. So if you want to write a basis that does not have any fractions in it, then you can scale this basis vector by any non-zero number and use that vector as the basis for convenience sake. So if I double both components of this basis vector, I get negative 1, 2 as an alternative basis vector. Okay, let's repeat this for the second eigenvalue that we found. R is equal to 2. Now you can expect something similar to happen here. In fact, if we go back to the first page, we've already stumbled across what the eigenvectors look like for this particular eigenvalue 2. It turns out that any non-zero multiple of the vector negative 2, 1 will be an eigenvector associated with this eigenvalue 2. Let's go ahead and confirm that. So we set up this system of equations, a minus r, where r is 2, so a minus 2i times a vector x, a non-zero vector is what we're after, is equal to the 0 vector. Going straight to augmented matrix form. So a minus 2i, that effectively amounts to removing 2 from the main diagonal. So removing 2 from the main diagonal of a, our new main diagonal becomes 1, negative 4. The other two entries are unaffected. So here's our matrix, a minus 2i, times some vector x is equal to the 0 vector. So an augmented matrix looks like this. Then we put this in a reduced row echelon form, which produces this matrix. And once again, we can see that we have a free variable at play. The only pivot position is right here, and so y, once again, is a free variable. So x plus 2y has to be 0. That tells us that x has to be negative 2y. And y can be itself. And it is the only free variable here. So our non-zero vector x has the form negative 2y, y, where I can factor the y out. This confirms that any non-zero multiple of this vector will be an eigenvector. And any multiple of this vector amounts to its span. And I'll just keep the vector as we found it because it had no fractions in it. Okay, now let's read down here. Notice that given an eigenvalue r, the corresponding set of eigenvectors is simply the null space of the matrix A minus Ri. If you recall, the null space of a matrix is a set of all vectors such that when you multiply to that matrix, you get the 0 vector back. So you could say it's a set of all preimages of the 0 vector. That is called the null space of the matrix A minus Ri, or you can say the kernel of the transformation whose standard matrix is this matrix A. Now, this is a vector space, and we call it an eigenspace, corresponding to the eigenvalue r. Describe each eigenspace above and identify its dimension. Now, like mentioned before, an abbreviation for eigenvalue, we can simply say eval. Similarly, eigenvector, we can say evec as an abbreviation. And for eigenspace, down here, we can say espace. These are accepted abbreviations of these terms. So in this first case, for the eigenvalue negative 1, what we found is an eigenspace. It is the span of the vector negative 1, 2. So the eigenspace for this first eigenvalue, r equals negative 1, is equal to the span of this vector. When you span a single vector in R2, you get a line in R2. And when there's a single vector in a basis, the dimension of this space is 1. Remember, the dimension of a space is equal to the number of vectors in its basis, not the number of components in the vector. Now technically to be an eigenvector you have to be a non-zero vector, but this space includes the zero vector. So you could argue that an eigenspace is the set of all eigenvectors combined with the zero vector, and that forms the eigenspace. And then for the eigenvalue of 2, this span is the eigenspace, or E space, for that eigenvalue. It is also a line in R2, and the dimension of this space is 1, because only one vector is needed for any basis. Okay, the rest of this lecture is going to consist of practice finding eigenvalues and their corresponding eigenspaces. Let's go to the next page. Find the eigenvalues and corresponding eigenspaces with dimensions for the matrix below. So this is a fresh matrix and we start from scratch. We begin by setting up the characteristic equation. So we want the scalar 0 to be equal to the determinant of this matrix A minus Ri, which means just remove R from the main diagonal. So -1 minus R and -3 minus R become the new main diagonal, and the other two entries stay the same. This is a 2 by 2, so calculate the determinant by multiplying the main diagonal and removing the product of the other two entries. Then FOIL this, giving us 3 plus R plus 3R plus R squared, and then minus -1, which becomes R squared plus 4R plus 4. And notice once again we do have the second degree polynomial. Let's see what kind of roots we get from this. This does factor. We get R plus 2 times itself, so we'll just write R plus 2 squared, which gives us a single eigenvalue. We'll list it twice to emphasize that its multiplicity is 2. Recall that the multiplicity of a root of a polynomial simply indicates how many times that root is a root. -2 is a root twice. So now we only have to find one eigenspace. So we'll let R equal -2. So we're trying to now solve A minus Ri, where R is -2, so that becomes A plus 2i times some non-zero vector x equals the zero vector back. So add 2 to the main diagonal of the matrix A, or you can look at this matrix right here and just change the R's to -2. Adding 2 to the main diagonal gives us a new main diagonal of 1 and -1, and the other two entries stay the same, and equals the zero vector. Put this in reduced row echelon form, which could be done in one row operation. Once again, we can see a free variable. Pivot position is in the x column, so y is free. The first row reads x minus y must be 0, so in other words, x has to be y, and y is free. One free variable. Therefore, our vector x has the form yy. We factor that y out, and we get any multiple of the vector 1, 1. So in this case, the eigenspace, or E space, for this eigenvalue, -2, is equal to the span of the vector 1, 1. Once again, this is a line in R2, and its dimension is 1, because there's only one vector in its basis, which of course corresponds to the number of free variables we had. Okay, the next page. Now we have a 3 by 3 matrix A, but the process is the same. Find the eigenvalues and corresponding eigenspaces with dimensions for the matrix below. So we begin by setting up the characteristic equation. 0 is equal to the determinant, and we remove R from the main diagonal. So you have 1 minus R, 2 minus R, and 2 minus R as the new main diagonal, and all the other entries stay the same. Of course, now we have a more complicated determinant to calculate, and I will use cofactor expansion along the first row, keeping in mind the matrix of signs. So targeting the first entry and crossing out its row and column, we have the 1 minus R in a positive position times the 2 by 2 determinant of the submatrix not crossed out. And then we target the 1, cross out its row and column. That's in a negative position, so I'll say -1, and I won't bother writing the 1, times the 2 by 2 determinant not crossed out. And then finally target this +1, cross out its row and column. So you have a +1 times the 2 by 2 determinant not crossed out. So this gives us 1 minus R times, now we have a 2 by 2 determinant, so we have 2 minus R times 2 minus R, so 2 minus R squared, and then minus a 1, and then minus, brackets, 2 times 2 minus r, minus negative 2, so plus 2, and then plus 2 times negative 1 is negative 2, and then minus 2 times 2 minus r. Now when you expand all of this and combine all like terms, I'll skip the steps of doing this algebra, but you do wind up getting the following third degree polynomial. And the goal now becomes to find the roots of this polynomial. We can use any factoring techniques we have at our disposal. So you can use the rational root theorem, where you do the p's over the q's to make a list of possible rational roots, and then you go to synthetic division to find a root, looking for remainders of 0, if you recall doing that in a college algebra course. But we're going to be satisfied if we use technology to find the roots of this by graphing this polynomial and looking for the roots from the graph. So let's go to Desmos and graph this polynomial using x as the input variable instead of r. So I typed in the polynomial y equals negative x cubed plus 5x squared minus 3x minus 9, and I get this graph here. There are two roots from the graph. The roots are the x-intercepts, negative 1 and 3. Furthermore, if you recall, if a polynomial crosses the x-axis at a root, like at negative 1 here, that suggests that the multiplicity of that root is odd. So it would have to be 1, 3, 5, 7, etc. But if a graph of a polynomial hits the x-axis but does not cross it, such as at x equals 3 here, then that is an indication that the multiplicity of that root is even. So it'd have to be 2, 4, 6, etc. But this is a third degree polynomial, and there can only be up to 3 distinct roots. Therefore, the multiplicity of negative 1 must be 1, and the multiplicity of 3 must be 2 to account for all the roots. Therefore, our eigenvalues are negative 1 and 3 twice. So the multiplicities are 1 and 2 for these eigenvalues, respectively. Now we must find the corresponding eigenspaces. We'll begin with the negative 1. So I'll go straight to an augmented matrix. That augmented matrix on the left side should have a minus ri, where r is negative 1. So it should have a plus I on the left side, and then of course the 0 vector on the other side of the equal sign. So add the identity matrix to A, which amounts to adding 1 to all the main diagonal entries. So the new main diagonal will be 2, 3, 3. And the other entries will stay the same. And now we put this matrix in reduced row echelon form. Now because r equals negative 1 is an eigenvalue, it means that a minus ri, which in this case is a plus I, will be a singular matrix, which suggests that we will get free variables. X is in R3, so it has 3 components, x, y, z. The leading entries are here and here. These are the pivot positions, so that suggests to us that z is free. The first row tells us that x plus z must be 0, so x has to be equal to negative z. The second row tells us that y minus z has to be 0, so y has to be z. And z will be itself, because it is free, and it is the only free variable. So our vector x can be anything of the form negative z, 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 where z is free, and if we factor out that free variable, we get any multiple of the vector negative 1, 1, 1. Thus our eigenspace for the eigenvalue of negative 1 is equal to the span of this non-zero basis vector. Of course, you could put any non-zero multiple of this vector in here as the basis. So you could, in theory, also write negative 2, 2, 2, or 1, negative 1, negative 1, etc. Any non-zero vector in the span will serve as a basis for the space. Well, graphically, we have the span of one vector in R3. So this will be a line in R3, of course, a line going through the origin. And since there's only one vector in this basis, the dimension of this space is 1. Okay, now let's find the eigenspace associated with the second eigenvalue we found, which is 3. So we'll set up an augmented matrix where we do a minus 3 times the identity, and then the 0 vector on the other side of the equal sign. So this time remove 3 from the main diagonal. It gives us a new main diagonal of negative 2, negative 1, negative 1. And the other entries do not change. Okay, now put this augmented matrix in reduced row echelon form. And notice this time we have only one pivot position right here. So we have two free variables, y and z. So the first row suggests that x minus a half of y minus a half of z must be 0. So in other words, that x has to be 1/2 of y plus 1/2 of z. Then y will be itself and z will be itself. And we have two free variables. So our vector x has the basic form 1/2 y plus 1/2 z as the x component, y is itself and z is itself. And now we will decompose this according to free variable and then factor out that free variable. So looking at the three components here, grab the coefficients of y. So you have 1/2, 1, and 0. And then plus z times, now grab the coefficients of z, 1/2, 0, 1. These two vectors are linearly independent of each other, and there's two of them. So this eigenspace will have two vectors in its basis. So it'll be the span of, now you can do any multiple of these vectors as well to form basis vectors, because if the two vectors are pointing in different directions in R3, then changing their lengths won't change that fact. So if you don't want the fractions, you can go ahead and multiply these vectors by some appropriate number so that there are no more fractions. So I'm actually going to double each of these two vectors I found here and use those as my basis vectors. So doubling the first vector I see gives us 1, 2, 0. Doubling the second vector gives me 1, 0, 2. And this would be our eigenspace. This is a plane in R3. The span of two R3 vectors that are independent will form a plane. And the dimension of this eigenspace is 2, because we needed two basis vectors, which of course equals the number of free variables that we had. I'd like to show you how to use technology to confirm some of this work that we're doing here. Let's go to the web, to wolframalpha.com, and begin to type in eigenvalues. And you'll notice a few different options pop up. And click one that has a 2x2 or a 3x3. I'll click this 3x3. And then let's adjust the entries. You enter in Wolfram Alpha, if you type in eigenvalues and enter in a matrix, you enter in the matrix by entering in a set of sets, where each subset represents the different rows. So let's change the entries in here to match our matrix. Okay, and then hit enter. All right, then confirm that you entered in the numbers correctly. And then let's look at the results. It's common to use the Greek letter lambda to represent an eigenvalue. We've been using r, but r or lambda are the two common choices for eigenvalues. And this confirms that the eigenvalues are 3, 3, and -1. And then also below you can see it gives us eigenvectors. Now, of course, these are not the only representations of these eigenvectors. So if you're doing this work by hand, and let's say for eigenvalue -1, you get 1, -1, -1 as an eigenvector. Notice that's different than the v3 that they're giving us, but your eigenvector basis should be a multiple of the eigenvector presented here. So the eigenvalues must be the same, but there are infinitely many different representations you can use for the bases for the eigenspaces. And Wolfram Alpha is just giving us some examples that can be used for v1, v2, and v3. All right, let's go to the next page. Another 3x3 matrix. Find the eigenvalues and corresponding eigenspaces with dimensions. Once again, we set up the characteristic equation. 0 must equal the determinant of, remove r from the main diagonal, so 2 minus r, 3 minus r, 3 minus r, and the other entries stay the same. This time, because I have a 0 at play in the first column, I'm going to do my cofactor expansion along the first column. And here are the three signs I need from the matrix of signs. So we have a positive 2 minus r being targeted, so I'll just write 2 minus r, times the determinant of the 2x2 not currently crossed out, which I'm just going to go ahead and calculate what that is. Multiply the 3 minus r times the 3 minus r, so 3 minus r squared, and then minus the -1 times -1, so minus a 1. Now I can skip targeting the 0 and go straight down to targeting this 2, cross out its row and column, and that's in a positive position again, so we say plus 2 times, and then the 2x2 determinant of the submatrix not crossed out, we have 2 times -1, which is -2, and then minus 2 times 3 minus r. And then when you multiply all of this out, I won't show the steps of doing that, but we wind up getting -r cubed plus 8r squared minus 16r. I could reach for Desmos and graph this and see what the roots are, but notice that there is no constant here. So I can do some factoring by hand in this case, practice our algebra skills. If I factor an r out, in fact, I'll factor a negative r, that leaves r squared minus 8r plus 16. And then I can try factoring that trinomial. It factors to r minus 4 times another r minus 4. So I'll just write r minus 4 squared. So our roots are, we have 3 roots here. Set negative r equal to 0, we get 0. So 0 can be an eigenvalue. And then the other 2 eigenvalues are 4 and 4. So again, 0 has multiplicity 1 and 4 is multiplicity 2. Okay, now finding the eigenspaces. For r being 0, we do a minus ri. Well, if 0 is r, then we do a minus 0i. Well, we just get a. So our augmented matrix would have this form in this case. So in this case, we're basically finding the null space of that matrix A unadjusted. Putting this in reduced row echelon form, we get, and as expected, we do have a free variable. The pivots are in the x and y columns, so z is the only free variable here. Row 1 reads x plus 4/3 z has to be 0, so we get x has to be negative 4/3 z. Row 2 reads y minus 1/3 z has to be 0, so y has to be 1/3 z, and then z is itself, being the only free variable. So our solution has the form negative 4/3 z, 1/3 z, and z. We can factor that free variable out, and we have negative 4/3, 1/3, and 1. This vector forms a basis for our eigenspace, so any non-zero multiple of this vector can also serve as a basis vector for the eigenspace. So let's go ahead and triple it and say our eigenspace, or E space, for our eigenvalue 0 is equal to the span of the vector, and triple this vector above, we get negative 4, 1, 3. Well, this is a line in R3 that passes through the origin, of course, and the dimension of this eigenspace is 1, because we have one vector in its basis, one free variable. And now for the second eigenvalue, r equals 4. So we're going to set up a minus 4i, augment it with the 0 vector. So remove 4 from the main diagonal of the matrix A, and we get negative 2, negative 1, and negative 1 as the new main diagonal. The other entries will stay the same. Now we put this matrix in reduced row echelon form. Identify the free variables. We have pivots here and here, so z is the only free variable here. First row reads x has to be 0. Second row reads y plus z has to be 0, so y has to be negative z. And z will be itself, being our only free variable. So our solutions will have the form 0, negative z, z, which we can factor out the free variable and get multiples of 0, negative 1, 1. So any non-zero multiple of this vector will serve as a basis vector for the eigenspace. We'll just use that vector itself. This again is a line in R3, and the dimension of this eigenspace is 1, which matches the number of free variables we found. Okay, let's do one more 3x3. Again, find the eigenvalues and corresponding eigenspaces with dimensions for the matrix below. Setting up the characteristic equation, remove r from the main diagonal, leave the other entries the same, calculate the determinant. Well, there's a lot of zeros in the first column, so that's where I'll do my cofactor expansion. So we have a positive 2 minus r times the 2 by 2 matrix not crossed out, which is just going to be 2 minus r times itself minus a 0. And this is the only product we need to do, because when I target the other 2 entries in that first column, we just get 0 each time. So this is a very simple determinant, and it's already factored. No sense in multiplying all this out. We simply get 2 minus r cubed. So there are cases where sometimes when you find the determinant of the 3x3 matrix, that you get a characteristic polynomial that's already partially or maybe even completely factored. So in such cases, continue to factor, don't expand, and then try to find the roots. But the roots here are all 2. So you have a multiplicity of 3 this time. So there's only one corresponding eigenspace we need to find. Let's let r be this eigenvalue of 2. Remove 2i from the matrix A and augment with the 0 vector. Removing 2 from the main diagonal, we get zeros as the new main diagonal. All the other entries stay the same. Well, this matrix is already in reduced row echelon form. The only pivot position is right here in the y column. So that means x and z are both free. So x can just be itself. Second row reads that y minus 3z has to be 0. So y has to be equal to 3z. And z is also free, so z can just be itself. And we have two free variables here, x and z. So our solution has the form x, vector x has to be, well, x is just x, y has to be 3z, and z is z. You must express your vector solution in terms of only the free variables, and then decompose. So we have x times, and then grab all the coefficients that you see of x, which would be 1, 0, 0, plus free variable z times the vector, grab the coefficients, 0, 3, 1. So these two vectors are linearly independent, and will together form a basis for this eigenspace. Again, because we're literally saying do any linear combination of them, and you get a eigenvector, provided that the eigenvector is non-zero. So the eigenspace for r equals 2, for eigenvalue 2, is equal to the span of, and I'll just use these two vectors as they're written. This, of course, would be a plane in R3, and the dimension of this eigenspace is 2, because we had two basis vectors, which matches the number of free variables. Now, in this lecture, we did not see any 3x3 matrices that produced three distinct eigenvalues, but if that happens, you simply have to compute three different eigenspaces. So you just repeat the process for every new eigenvalue. Also, the process continues to generalize for 4x4s, 5x5s, etc. A couple last things to note down here at the bottom. Note that the dimension of an eigenspace cannot exceed the multiplicity of the corresponding eigenvalue. Let's examine that for each of the problems that we did. So here was the dimension of our eigenspace, was 2, and it cannot exceed the multiplicity of that eigenvalue, which is 3. An eigenvalue with multiplicity 3 will have at most 3 vectors in the basis of its eigenspace. In this case, we only had 2. Looking at some of our previous problems, eigenvalue 0 had a multiplicity of 1, so it can have no more than 1 for its dimension. So basically, for every distinct eigenvalue, there will only be one vector in the basis for its corresponding eigenspace. Now for the eigenvalue 4, we had a multiplicity of 2 and a dimension of only 1. But the maximum dimension would have been 2, since that is the multiplicity of 4. Looking at the previous example, eigenvalue 1 had a multiplicity of 1, therefore you're going to have a dimension of 1. Eigenvalue 3 had a multiplicity of 2, and it also had a dimension 2. So there are cases where the dimension will match the multiplicity, but it cannot exceed it. In this 2x2 case, we had a multiplicity of 2, but a dimension of only 1. And in this case, this eigenvalue -1 had a multiplicity of 1, therefore has a dimension of 1 for its eigenspace. And this eigenvalue of 2 had a multiplicity of 1, therefore a dimension of 1 for its eigenspace. And now one final comment. The theory that encompasses eigenvalues, eigenvectors, and eigenspaces is known as spectral theory. Just for your information. All right, this wraps up our first discussion on eigenspaces. The next topic, we'll discuss eigenspaces some more.